Please get started for our late afternoon session here. If we can maybe close the doors. Jan, can you please close the door? Thank you. So this session will be focused on the GEFSv13 version developments and its current status, and how are the stakeholders, the main stakeholders within NOAA and external to NOAA plan to use it. They may also be talking about the current use of the previous version, the existing operational version, GEFSv12. And we also touch upon some of the challenges and other issues in our GEFS development, which will probably should get addressed with the future version, which is GEFSv14. So we have 7 talks, and I'd like to get started by inviting Dr. Bing Fu to come and talk about GEFSv13 status and challenges. Dr. Fu comes to us from the Environmental Modeling Center.
Thank you, Arsham. Good afternoon, everyone. I'm very happy to be here to give you an update about GEFSv13. Yeah, before I start, I need to give an acknowledgement to all my colleagues who have been working on GEFSv13 project. Yeah, this is the outline. First, I'm going to show the configuration for GEFSv12 and GEFSv13. So the difference, the updates. I want to show the focus for GEFSv13. One of the focuses for GEFSv13 is to improve subseasonal to seasonal forecast. And after that, I will give you a very brief introduction for GEFSv13 prototypes. In particular, I introduce EP4 and EP5, which include aerosol coupling. And I think the major focus for this talk is EP4R2, because this is going to be the last ensemble prototype for GEFSv13, and it is targeting GEFSv13 reforecast. And last, I'll give a summary and show the challenges for GEFSv13 development. So this table shows the configurations for GEFSv12 and version 13. In the middle, you see the version 12. And I think the major, of course, there's a lot of updates from version 12 to version 13. You see the physics updates and DA, Sulagna physics, and the model vertical resolution, etc. But I think the major focus, or the major change you see here is for GEFSv12 is uncoupled model, and for version 13 is have ocean ice coupling. Basically, will be expected to improve the subseasonal forecast. The GEFS ensemble prototypes is based on the coupled model, UFS coupled model prototype. You are aware there's multiple coupled model prototype from P1 to P8 and higher resolution prototype HR1 to HR3. For ensemble prototype, like EP1 is based on coupled model prototype 5, and the EP2 is based on P7, EP3 based on P8, and the EP4 and EP5 based on HR1 and HR3. And you see on the right, you see the time step for each ensemble prototype. Usually, it takes about 8 to 11 months to finish one ensemble prototype. You need to configure the model, develop a workflow, and run the experiments and evaluation. So it takes a long time. This table shows only EP4 and EP5, because starting from EP4, we have aerosol coupling. And also starting from EP4, we have multiple small experiments or small prototype, you can call, you name it. You see here, EP4, we have EP4A, EP4B, C, and D. Basically, the small mini set experiment usually just do some sensitivity test, or there's some bug fix, or we change the initial conditions. Like, for example, EP4A, we have a bug fix. Then we go to EP4B to fix the bug. And if you see EP5, we see EP5, R1, R2. Because starting from EP5, R1, we are using replay conditions. But previously, we have been using GEFS version 15 conditions for atmosphere. And starting from EP5, R1, we turn to a replay condition. And also, you see on the right, you see we run a 2-year experiment for EP4 and EP4B, and also EP5, R2, we have 3-year experiments. From EP4 to EP4B, you see the changes here. EP4 is a uncoupled model. No, sorry. EP4 is no aerosol coupling. And the EP4B have prognostic aerosol with observed emission. You see the both fonts, so the difference. And we have mini cell run EP4B is change the observed emission to blending emission. You see the on the bottom, you see the blending emission, the definition or the detail. And EP5D is based on HR3 physics. It's also mini set. And the EP5R2 is a full set prototype. We have 3 years run and plus the dynamo here. I will introduce EP5R2 for some details later, using replay induced condition. So basically we have several experiments for this EP4 and EP5 series. This is some results from EP4 and EP4B. I want to show this figure, compare the impact from aerosol coupling. See on the left is GEFS basically it's a reference or it's a baseline. This is so the average AC score for 500 millibar height, northern hemisphere and the southern hemisphere on the bottom. It's 2-year experiments. You see, this is the blue, it means it's better than GEFS 12. And if you see the bold text means significantly better. And from this table, we see in the southern hemisphere, EP4 and the EP4B for week 3 and week 4 is not as good as GEFS 12. And for week 3 and week 4, if we have aerosol coupling, is significantly worse in the southern hemisphere. But in the northern hemisphere, everything is good. So this EP5R2 basically is the very likely is going to be the last ensemble prototype for GEFS 13. And this is targeting GEFS 13 reforecast. And based on EP5R2 is based on HR3 physics. Our model has here. And the initial conditions from DSL replay initial conditions, long start from F03. And we have 11 ensemble members. We have 35-day forecast, and also a portion of the experiment have 48-day forecast. See, 3 years experiments, and for dynamo period, we have 48-day forecast. So evaluation is still ongoing, but we have finished several presentations. And also I want to mention here, we have multiple centers involved in these evaluations, not only EMC, CPCO, WP, WPC, SPC, PSL. We have finished a few presentations in GEFS 13 T2O meetings in this month and last month. And then we are going to have several other presentations in September, in the middle of this month, the next T2O meeting. So far, overall, the model performance shows improved compared with GEFS 12. That's good. That's what we want to see. Just so very preliminary results from EPFR-R2, and you're going to see more results from EPFR-R2 in this session in the following presentations. Here shows the 500 millibar high CRPS skill, actually CRPS skill. On the left is northern hemisphere, on the right is southern hemisphere. You see the black, the GEFS 12 in black, and the EPFR-R2 in red. You see both hemispheres we have input the CRPS skill. And for this is a zonal wind, 10-meter zonal wind bias. So also see GEFS 12 has a little bit easterly biases in northern hemisphere and the southern hemisphere both. But for EPFR-R2, we see the biases is pretty good. You see there is almost zero line here. This shows zonal wind at lower level and upper level because current operation GEFS 12 has a little bit over dispersive for the lower zonal wind. You see here, the black, we see the over dispersive here. EPFR-R2 will have improved this over dispersive. We see the reduced over dispersion. And also we see the RMIC has been reduced in EPFR-R2, especially for the lower level, and for the upper level, 250 millibar. We also see the reduction of RMIC, but spread is pretty similar with GEFS 12. This is a scorecard for EPFR-R2 and GEFS 12. Basically, you see the green means better and the red means worse. And see the hopefully you can see the gray, or this is a green, I don't know, the color is different from the laptop. It's neutral. You see here, basically overall, EPFR-R2 has improved compared with GEFS 12, especially for AC score, the top. For RMIC, overall it's improved, and but for temperature in the tropics, a little bit degradation. For model bias, it's mixed results. Some degradation you can see, notice here near the boundary layer, PBR, and some other level probably good. It's good. This is horizontal 2-meter temperature bias estimation. On the left is GEFS 12 laptop. This EP4 is based on HR1 physics, and EPFR based on HR3 physics. You see the biases is pretty similar to GEFS 12 and the EP4. See here is a circle here, where it's basically GEFS 12 and the EP4 here. You see the warm bias, the EPFR-R2. So here is a little bit cold bias. But for high latitude, it's pretty much different. GEFS 12 and the EP4, you see the cold bias here. The high latitude in the northern hemisphere, you see the little bit warm bias in the EPFR-R2. This is for week 1. As here, the bottom shows the difference between the EPFR-R2 with compared with GEFS 12 and the EPFR-R2 with EP4. For week 3 and week 4, the pattern is pretty similar, but only the magnitude has increased. The warm bias in the high latitude still there. You quick see this slide shows the corners precipitation evaluation. On the left is CRPS. On the right is a mean error and absolute error. The EPFR-R2 consistently has a lower CRPS compared with GEFS 12, and also has a less error than GEFS 12. This shows also corners precipitation, the Bright score and the Bright skill score. On the left is the Bright. On the left is 1 millimeter category precipitation. You see the both score is consistently better for EP5R2 compared with version 12. On the right is 10 millimeter precipitation is still EP5R2 is better than GEFS version 12. So you're gonna see more results from other presentations in this session. I'll give you a very quick summary. So GEFSv13 is going to be a fully coupled model to further improve subseasonal to seasonal prediction. And we have finished the last ensemble prototype, EP5R2. Evaluation has been carried out by multiple research centers and other stakeholders. And the preliminary results show overall better performance of EP5R2 compared with GEFSv12 in some metrics, but we also noticed some degradations. For challenges, we have a lot of challenges for GEFSv13 development. Here's a list of some of them. One of them is ensemble workflow development is lagging behind the progress of model development. So all the ensemble prototypes are using a temporary workflow to run the experiments. For future operational, we have to switch to a global workflow. And because of this limited computation resources, all the experiments are carried out using 11 ensemble members, but for operational GEFS, it will be 31 members. So we have less ensemble members, and also need code optimization for running longer time period experiments, like 48-day forecast. And another one is coupled DA system is still under development. There's no initial conditions from coupled DA available to be used for ensemble experiments, but in the future, operational GEFS is going to be a coupled DA, so we have different initial conditions between the experiments and the future operational GEFS. On the right, you see another challenge is we have a lot of model updates from one prototype to another one. And for each upgrade, we have the model physics update, and basically the model physical tendencies can be changed. Because we have SPBT stochastic scheme, it really depends on the model physical tendency. So each update we have to adjust the SPBT, tuning the parameters so to get the reasonable results. And also one of the challenges I also need to mention is the plans we implement GFS version 17 and the GEFS version 13 at the same time. And we are going to run the retrospective at the same time. So it's another challenge for resources coordination. And also we have to do the field office have to do the field evaluation at the same time for both GFS and GEFS. So it's another challenge. So we say there are a lot of challenges. I just leave some of it. I think that's all. I'm happy to take any questions.
Yeah, let's leave questions until afterwards because we're running a little late. Thank you, Ben. Next we have Mark Fresch from the WP.
I'm Mark Fresch, Office of Water Prediction, and I'm going to talk about our use and requirements for reforecasts. Next slide, please. Or do I have to do that?
No, you could drive with the clicker.
Okay, thank you. Let me just take this off. So our current reforecast requirements are largely driven by the HEFS Hydrologic Ensemble Forecast Service on the left. There's about 3,000 major river locations that HEFS is running in operations. Those are the dots on the left. And then in the future, we may also add national water model considerations. So that's a big TBD, and that runs on stream flow, provides stream flow predictions at like millions of very small stream sections. But the point is that it could possibly be both in the future, and now it's just HEFS on the left. And then a quick introduction, just to let you know what HEFS is. So a number of years ago, the National Weather Service was running an ensemble hydrologic forecast called the Ensemble Stream Flow Prediction, which only used climate observations as a forecast. And since then, that's been replaced by the HEFS, and HEFS has the advantages on the right. And the biggest one, of course, is that it has the input forecasts from actual weather and climate models. In real time, this is how HEFS works. There's a number of options for the models that you would like to use, and you can use a blend of these on the left, like the WPC forecast. RFC has a UPF forecast based on that. GEFS, that's our bread and butter. It can also use CFS-V2 and climatology. Those all go into a preprocessor called the MEFP. And then there's a post-processor in the top middle in blue, which corrects biases in the stream flow. And so your takeaway is that we can use all of these forecasts in real time. Then moving on, the way we use reforecast is in three ways. There's decision support by users, which requires 30 years of daily reforecast. And the GEFS-v13 is basically our baseline for what we're doing as far as reforecast. Sophisticated end users use this to create, and including ourselves, create hindcasts of HEFS for calibration and validation of their systems. FIRO is basically a concept where they use forecasts for reservoir operations, forecast-informed reservoir operations. We use HEFS for validation. Again, 30 years needed. We have a lot of investments in approving HEFS. So we need to validate that and guide our operational use and improvements. The reason why we need 30 is primarily because of extreme events. I'm going to show you a slide with a couple study links, which we did. And as I said, we're committing a large number of resources to improve HEFS. So those validation efforts are important. And then lastly, we also, HEFS needs calibration. Using reforecast, the requirement there is a bit less, only 12 years of daily reforecast. And that is calibration of that one section, which merges all the forecasts from the different sources using statistical means. So I wanted to go into, in the next talk, you're going to hear a similar, more in-depth talk about one of these sophisticated users, but this one's a good one too. I'll start with this. Russian River, which feeds Lake Mendocino. That's an example of forecast-informed reservoirs. This lake and this is on the Russian River, just north of San Francisco, if you're familiar with it. So this is a big deal in an area of the country where water is such a critical resource. And this reservoir is supported by multiple agencies at the local, state, and federal level. So it's hard for them to change the way they operate their reservoir. This is frequently the case, and at least in my experience, when you have a lot of agencies involved, to change the way they do things. So they need some good evidence to change from their old way of operating to using HEFS forecast. And in this case, the slide shows the storage of the reservoir with 100% towards the top, which is optimum across a 25-year period. So the best would be if it was flat straight across. The blue here is the current operations, and the yellow is if you had perfect forecasts, and in between there, close to the yellow, is if you used HEFS forecasts. So we did a pretty good job of optimizing the forecast operations there. Another sophisticated user is New York City. Their water supply is called the Department of Environmental Protection. The next talk is more about this. Let's just say, as you'd expect, it's a big water supply, and they use real-time HEFS forecasts, and they use 30 years of HEFS Hindcasts for calibrating and validating their decision support tool, which I call the operational support tool, I think. Anyway, in doing that, they have been able to avoid over 10 billions of water filtration costs within the New York City water supply. Is that a 2-minute warning? Oh, yeah, I'll be done.
Yeah.
So these are 2 studies that we did, which are the basis for our requirements. And basically, what we found was in the first study was in order to get stable metrics when we do validations, we need X number, in this case, 30 years of daily, especially when it comes to the more important sampling of extreme events. And then we had a study with PSL and the University of Wisconsin in Madison, where we tried to do some sophisticated thinning using methods that they created. And there looked like there was some hope, but there really hasn't been any follow through. So there's we're not hard-headed. We're willing to listen and adapt as needed. So we're planning to use V13 forecasts in the same way, 30 years. Validation, sophisticated users. And I think there are ways that we can adapt, but it's going to take a little bit of time if we want to reduce the amount of reforecasts that are created before the model goes live. I think that's really the crux of the issue that we'd have. Any questions?
Thank you. We can take a question while we switch to the virtual speaker next, right?
Yeah, I believe so, yeah.
Any question?
Yes.
So when you talk about the GEFS going into HEFS, to run that through MEFP, or you kind of individual ensemble numbers?
Will you run the GEFS through MEFP?
Is that one run of the GEFS or all?
In real time, it's using the operational model run.
I don't know. I'll check.
By default, it runs once a day using the 0Z, but you can configure it to run more often if you want.
Yeah.
All right, thank you. All right, yeah, thank you, Mark. All right, so next we have a change to virtual presentation by Matonse from the Bureau of Weather Supply in New York.
If you're online, I'll share your screen.
Yeah, sorry, maybe you can't hear us. So could you share your screen, please?
Yes, I'm trying to share my screen now.
Okay.
Okay, thank you. Can you hear me?
Yeah, we can. Thank you.
Okay.
Yeah, the floor is yours. We don't see the presentation yet, though.
Okay. Entire screen, yes. Can you see my screen?
No, we do not.
I thought I was sharing my entire screen. Entire screen, share.
There we
All
go.
right, all right. Yeah, now we're good.
Do you see? Do you see it
Yeah.
now? Okay.
We see your
Yeah,
entire.
yeah,
Okay.
then expand it, yeah.
Okay. Let me go in the presentation mode.
Okay, that's great. Thank you.
Okay. Thank you. Good afternoon, everybody. I will start by thanking my co-authors who produced and worked on most of the materials that I'm going to be talking about today. I also want to thank Mark Fresch for helping me at least pass a few slides by introducing the New York City water supply.
We lost your screen there.
Yeah, we lost your shared screen.
Somebody else had the same thing. They don't share the screen.
Slides too.
Okay, let me.
Do you have the slides?
I have the slides.
Do you want us to run the
We
slides
could drive if you like.
and let us know when to switch the slides?
Okay.
Okay.
All right, good. I'll share then. This, I believe, there we go. All right, well, let's, there, let me go to. There we go. Back. All right.
Okay. All right, how's it look on your side?
Yeah, it's perfect.
Yeah, just let me know when you need to change them.
Okay, let's go to the next slide. I was going to talk a little bit about the New York City water supply, but I will skip that. I will talk about the operation support tool. And then I will jump into the collaboration with the Northeastern and Middle Atlantic River Forecast Center, as well as the Office Water Predictions. Then I will talk about the importance of NWS products and the way we are using them. And I will end with our goals and priorities. Next slide. You can skip this one. Next slide. So the New York City Operation Support Tool, or OST, is a software that allows us to evaluate all aspects of New York City water supply system. OST integrates near real-time data and ensemble hydrological forecasts. The core of OST is the OASIS system model of New York City water supply system and the Delaware River Basin. And we also have, at the selected reservoirs, water quality W2 models that simulate turbidity and water temperature. We use OST in two different ways. One is to create short-term ensemble simulations for operational guidance. The second is to create long-term runs to generate output to support capital planning, rule testing, and climate change impact assessment. Users across the different offices of the Bureau of Water Supply can access the system through simultaneously through a graphical user interface. Next slide. Our collaboration with the National Weather Service goes back to 2013. when the New York City DEP asked NWS to develop the first ensemble forecasts for use in OST, which was at the time under development. The first product was delivered in 2014, GFS 10, HFS, just the raw forecast and using 38 traces. That collaboration continued since then until today, and I can only be happy for us to continue with that collaboration. Currently, as a result of that collaboration, currently we are using GEFSv13 GFS with 6 traces. MARF is replacing API with the Sacramento hydrological model for the HFS forecast. NWS is improving NERF's HFS MEFP for high precipitation. Our current products includes not only the raw forecast, but also post HFS, and as well as Mike mentioned, updated historical simulation and hindcasts. Next slide. How do we use HFS ensemble forecast? We use it particularly for what we call positional analysis of OST. In positional analysis, the run starts today and it can go up to a year from today in the future. And that's the kind of run that we use to support reservoir operations. The type of models that we run includes open run. That means we start OST with current status of the system and the inflow forecast, and we let it run with the rules that are embedded in the model. The second is the current operations. Sometimes the management has already decided how they want to run operations for 1 or multiple weeks. And we take that information and we force the model to implement those operations. These are current operations. But the model is also used to test operational alternatives. It also provides output to support infrastructure repair projects as well as infrastructure shutdown, like the one starting in October, where we'll be shutting down the Delaware aqueduct that provide more than half of the water that goes to the city. And it can take between 5 and 8 months. The bottom right slide shows how do we use the ensemble forecast to drive Oasis and the W2 models. And from that generation, we produce a probabilistic output that we share and discuss with managers and operators. Next slide. HFS ensemble forecast is also very important because it supports the flexible flow management program, through which program we release water when it is available, and conversely, we release less water if less water is available. This is part of the current 2017 flexible flow management program that is in place, and it guides us to make releases to the Delaware River Basin. Using HFS inflow, we accumulate inflows through June 1st and use that to calculate the Delaware Basin New York City reservoirs mass balance, and which result in available release quantity accumulated through June 1st. We then estimate the current PSNN release target, and together with that target and the current storage availability to know if we have how much water we have in the reservoirs in Pepacton, Cannonsville, and Neversink reservoirs. We then select a release target schedule like the one highlighted here in green, and that is based on tables that are part of the 2017 FFMP. Next slide. We also, our W2 models require meteorological forcings. that include air temperature, dew point, wind speed, wind direction, solar radiation, precipitation. The W2 water quality models are two-dimensional hydrodynamic models that simulate turbidity and water temperature, as I mentioned before. Next slide. Now we also use historical simulations to develop our own ensemble post-processor. The first one was APP-V1, based on general linear model like ENSPOST. This development started in 2012, and this APP was ready for use in OST in 2014. Sooner, when we started using APP-V2, we started comparing the performance of APP-V1 post-process flows retroactively in flows with observations. And we also added to that comparison the raw forecast. The right slides on top show the raw forecast Colebrook scaled to Alabama, a 3-day lead time. And the one at the bottom shows the APP-V1 post-processed. And we soon realized that for some location, and for some location more often than others, the APP was adding high inflow events that were not in the raw forecast. And the same way, in some instances, it was missing high inflow events that were present in the raw forecast, but were not showing in the post-process forecast. This was a big concern for us, and it was also a motivation for us to start working in further developing our ensemble post-processors. The first of them was APP-V2. We work together with John Chaki to develop APP-V2. This was ready in 2016, and since then it has been in use in OST together with some locations that are using as post-processed from the National Weather Service. So most recently, we start working with the RTI to develop quantile-to-quantile mapping-based APPs, as well as artificial intelligence-based APPs. This is a work in progress. Next slide. This slide shows an ensemble forecasting for diagram. The way we use the historical simulation together with observation to develop our post-processors that are then run using the raw forecast. And we also have the alternative to use HEFS and post forecast. What we also do is to use the historical Hindcasts to do, we also perform an ensemble verification for each of these post-processors run at each of the OST forecast locations. And we then combine different post-processors in what we call mixed ensemble forecast post-processor, or just mixed APP. So our mixed APP is a combination of different APPs selected based on performance evaluation for each forecast location. We realize that some of these APPs are good in, for example, post-processing Skohari raw forecast than exposed or APP-V2. And that's the one that we select for that particular location. Next slide. This is my last slide. Our goals and priorities continue to be, or to seek, HFS forecast still improvements beyond day 15, if possible. Looking forward for GEFSv13 and V14 HFS, as well as SFv1. our priorities are in the row and ex-post forecasts, meteorological forcings, historical simulation, as well as hindcasts. We plan to continue improving our post-processors and look for ways to explore blending forecast, explore seasonal and regime-based forecast options, and we hope that during this workshop we will learn from other users who may be using these kind of approaches. We are also going to discuss with our partners, including the National Weather Service, to find ways to continue benefiting from this extraordinary collaboration and look at the implications of future collaboration in light of our, to support us in reaching our goals and priorities. Thank you. Next slide.
Great. Thank you very much. It's great to see how GEFS and other products are being used downstream. With the interest of time, let's move on. We got another virtual presenter, Robert Long, CPC, talking about evaluation of the GEFS Hindcasts. Robert, are you online?
Oh.
Yes, I am here. Can everyone see the screen?
Yes, we do.
Fantastic. All right. So good afternoon, everyone. I'm Robert Long. I'm a contractor with ERT supporting the Climate Prediction Center, and want to thank everyone for the opportunity to share some just initial evaluations of the GEFS13. This is the EP5 R2 Hindcast mini data set that Dr. Bing just referenced earlier in the session. And I want to compare the evaluations that we did of GEFS13 to evaluations of 3 reference hindcast systems, namely the GEFS12, the current cycle of the ECMWF hindcast, as well as CFS version 2. And I'd like to thank my CPC colleagues, Wanchu Wang, John Gottschalk, and Mingyue Chen for their support of this work. There are 3 main goals for this talk. First, we're going to identify and quantify the hindcast scale in that GEFS13 mini data set, looking at forecasting temperature and precipitation on the subseasonal scale. And I'm going to include week 1 in this presentation as well. Next, we're going to present the GEFS13 scale within the context of these other reference hindcast systems, and then make some general statements about the GEFS13 hindcast performance. And then lastly, we'll kind of dive into some regional and seasonal variability in the GEFS13 hindcast scale. For regional variability, I'm going to divide the CONUS evenly into 4 quadrants and calculate skill scores within each region. And then for seasonal variability, we'll take a look at how the skill varies over the 4 boreal seasons in 3-month increments. So here is a breakdown of the data used for each evaluation. The cadence of the GEFS13 hindcast mimics that of the GEFS12. In other words, it comes out about once a week. But the GEFS13 hindcast only spans 2 years. So for GEFS13, we have just over 100 forecasts over this period. For the 3 reference models, I chose to use a full 20-year period to prepare the climatological means and bias correct the forecasts. And we did this so this approach would give us the most accurate capture of the hindcast skill in the reference models. And by doing this, we can see how GEFS13 stacks up to that degree of skill. All of the data used in this study are at half-degree resolution, and we used ensemble means, and we prepared weekly forecasts to calculate the skill metrics. So a quick follow-up on the GEFS13 hindcast mini data set. So for hindcast evaluations, we need to define the climatology or define the background and correct for bias. This is a straightforward process when you've got a 20-year record or longer. With a 2-year record, not so much. The challenge is that the model mean bias and the interannual anomalies cannot be separated. There are multiple ways to derive a background when you have a short period like this, and each one has its own strengths and its own limitations. My colleague Mingyue performed a similar analysis on this data, and her approach was to prepare the background by using a harmonic truncation of the annual time series. My approach was to use a running mean with a 7-week window. Both methods result in anomalies that are intra-seasonal only. In other words, the model bias and the interannual anomalies are going to be included in the running mean. They're going to be included in our background. So one such impact of this is that bias from the ENSO signal, for example, cannot be filtered out of the hindcast. And the plot on the lower right-hand side that you see shows the presence of both a La Nina signal as well as an active El Nino signal during our GEFS13 mini dataset period. So with that acknowledged, here are some of the results when we'll start with temperature. So this is a look at absolute mean bias into meter temperature. What you see on the left are spatial plots showing annual bias in GEFS13 for weeks 1 through 4, where week 1 is in the upper left, and then week 4 is down in the lower right. And even though the hindcast is only 2 years, we see persistent cold bias across the eastern United States, which is consistent with the cold bias that's observed in GEFS12 hindcasts. On the right-hand side there, you see 3 bar charts, and we're going to see the same layout for the next several slides. The 3 bar charts in the upper right-hand corner, they show the kind of the intermodel comparison. So we've got the GEFS13 skill shown in blue, and we compare it to GEFS12, which is seen in red, ECMWF there in yellow, and then the furthest to the right is CFS there in green. And the take-home message is when we compare these models with respect to bias, GEFS13 exhibits similar skill as the 3 reference models. The middle chart shows our GEFS13 bias per region of CONUS. And we see the slightly higher biases in the Northwest and in the Northeast as a result of that cold bias. And then in the bottom right-hand corner, the GEFS13 skill by season, where we have higher biases occurring in the winter and spring, and a little bit less in the summer and fall. When we take a look at root mean square error for temperature, the annually averaged spatial plots there on the left show that the lowest error occurs in the southeast at each forecast lead, and we see the highest square error kind of over the northern high plains there of Idaho and Montana. In the upper right-hand corner, GEFS13 exhibits less error than GEFS12 and CFS, and is similar to ECMWF, again, at the first couple of weeks. And this result, again, coupled with the result from the bias, this is encouraging for the viability of using GEFS13 hindcasts in subseasonal applications. When we take a look at anomaly correlations, these are promising results as well. The GEFS13 has the highest correlations relative to the other models in weeks 1 through 3. They're very close, but GEFS13 is just slightly higher. And when we look in the lower right-hand corner, we see that the correlations are consistent across the 4 seasons at each forecast lead. The correlations decrease sharply from weeks 3 to 4 in GEFS13, but that is the case with all of the hindcast systems. When we look at precipitation, the story is very similar. The error-metric results with precipitation are consistent with those that we just saw for temperature. The chart on the left shows that GEFS13 has slightly lower error than GEFS12 and CFS, and higher than ECMWF at all leads. And these findings are consistent with the plots from Eric Sinsky that Bing just showed earlier in this session. When we move on to looking at correlation skill for precipitation, it's kind of a mixed bag. The GEFS13 shows similar to maybe slightly better correlation skill at weeks 1 and 2, but no skill at longer leads at weeks 3 or 4. And again, this is consistent with what we find when we look at the other hindcast models. So to summarize, the GEFS13 hindcast mini data set that we have does show comparable skill to hindcasts of much greater sample size. We had we had basically 1,000 forecasts that we evaluated for the GEFS12, for ECMWF, and for CFS, versus only looking at about 100 for the GEFS13. But we saw comparable skill for both temperature and precipitation. And it's quite promising that the GEFS-13 system exhibited similar skill when we compared it to Hindcast systems that were properly bias corrected with long-standing climatologies. Since the GEFS-13 Hindcast period is only 2 years, defining the background is a challenge. And as a result, that kind of limits our confidence in making robust conclusions about the GEFS-13 Hindcast skill. So we'll hold off on making a definitive declarative statement about the GEFS-13 performance until a longer Hindcast becomes available. But I wanted to kind of wrap up on a positive note and say that it's encouraging that both Mingyue and I found that GEFS-13 exhibited less error and higher correlation skill than GEFS-12 and CFS, despite the fact that we took different approaches to determining the Hindcast background. So the key takeaway from all this is that we're cautiously optimistic that GEFS-13 Hindcast can improve probabilistic forecasts of hazards such as drought, which Hylon referenced in her talk yesterday, as well as extreme rainfall events on a subseasonal scale. So thank you very much. And if there's time, I'll take a question or two.
Yeah, thank you very much. Very encouraging results. We are still a little bit behind on time, so we are going to move on. But please ask email or Slack. So next we'll be talking about the NJU, me and Chen.
There we go. We'll go back. There we go.
I'm Mingyue Chen from NCEP. So I'm saying that in this presentation, I'm going to show the MGO vulnerabilities in the NCEP GEFSv13 experimental forecasters. The co-authors are Wang Overall and John Gutchison, the same group of people in the previous Robert's presentation. So, thanks for their contributions and support. Okay, the background of this analysis is well known that the Mingyue oscillation is a dominant mode of tropical convection variabilities on subseasonal time scales. It moderates the weather and climate activities on the global. So enhancing MGO prediction capability remains a premier objective in the development of dynamical models for subseasonal and seasonal forecasters. The objective of this analysis is to provide an assessment of the NCEP GEFS EP5R2 experiments in forecasting multiple MGO events during the dynamo period, and compare its performance with the current version NCEP models and ECMWFs. During the dynamo time period from early October 2011 to mid-January 2012, model forecasts of GEFSv13 EP5R2 are available on Mondays and Tuesdays, a total of 31 initial days. Current version GEFSv12 was on Wednesdays, a total of 16 initial days. CFSv2 forecasters are available at the same initial days as the EP5R2. ECMWF's forecast available on Sunday and Wednesdays. We focus on the scale assessment of tropical OLR precipitation and the MGO with the Hydrogen Index IMM. The scales are based on ensemble means of 11 members. So keep in mind, these comparison may be uncertainties of there due to difference in initial days and the number of initial days. Okay, first look at the tropical variations in the observation. This slide shows observed OLR precipitation over equatorial Indian Ocean to the maritime continent from October 2011 to January 2012. So we can clearly see the three well-organized eastward propagating MGO events initiate in the Indian Ocean in October, November, and December. We will just mark as the MGO 1, 2, and 3 in the analysis. So next, we are going to check how these three events are predicted in the forecasters starting from initial days near to the time when convection was initiated in Indian Ocean. Okay, here is the forecasters equatorial OLR forecasters and observation for these three MGO events. This 30-day forecast starts from initial condition on or near October 20th for EP5R2, GEFSv13, and version CFSv2, and ECMWF forecasts. And here also I show the observations as a reference that we can compare to. For these October events, for all models captured tropical convection variability in the first 10 or 15 days. After that, at anomalies, the anomalies fed off, or the anomaly didn't propagate to the east. The seventh law, the middle law, is for the events of November or MGO2. So the 30-day initial 30-day forecast from initial date near or November 14. So for these events, we can see the EP5R2 and the ECMWF forecast that capture the eastward propagating convections for entire events. And both forecasters better than the other V2, other model V2 and CFSv2. Although the EP5R2, the propagating scale a little bit slow compared to the ECMWF and the observation. And for the December events, the initial conditions are on or near December 15th. So again, both EP5R2 and the ECMWF forecast are better than the other two models. So overall, the GEFSv13 looks like the amplitudes were too weak. The CFSv2, the propagation are too slow compared to the other models and observations. And the EP5R2 and the ECMWF comparable and both perform better than GEFSv13 and CFSv2. For the precipitation field, the comparison is similar to OLR. I'm going to skip this slide. Okay, this slide is a summary of correlation scales for these three MGO events. The left channel is for the OLR, middle one is precipitation, and the right one is the IMM index. So consistent with the spatial map, we just see that both EP5R2 and the ECMWF better than this black and blue bars. The scales are better than the CFSv2 and the GEFSv13, the origin and the red bars. EP5R2 and is comparable to ECMWF. Okay, these correlation scales are for the forecast for only 3 initial days for predicting these three MGO events. So next, I'm going to check how the forecast scales with all available initial data. Here is just the traditional MM scale lead time variation diagram. The left side is for correlation. The right side is a root mean square error. That is based on all forecasters available and all the 4 models in the comparison. So the correlation curves looks like a little bumpy because of limited sample size. But we do see the variation tendency from this scale maps. So in the first 10 or 15 days, both EP5R2 and ECMWF has similar correlation scales and better than the GEFSv13 and CFSv2. Then after 15 days, the EP5R2 falls behind the ECMWF. And after 20 days, the GEFSv13 have a big jump. The scale shows better or similar to the ECMWF and the GEFS. That is just a matter of sample issues since it's only 16 forecasters available. For the root mean square errors, the variation are similar to the consistent with the correlations. Then here is the scales lead time diagram separated for OLR, Sonowin U200, UH50. So to check for each of these variables contributed to the IMM scales shown in the slide before. So overall, EP5R2 and ECMWF are comparable and both perform better than the other 2 models of the OLR and the U850. For the U200, there the EP5R2 keeps similar scales with current version V12. Well, we can see here the low scales in the EP5R2 compared to the ECMWF at longer leads after 15. So this is maybe the cause for the root mean and the IMM scale shown in the previous slide. Then the GEFSv13, the scale jump mainly come from the U850. Okay, in summary, the GEFSv13, this is experimental forecast EP5R2 reasonably capture the variability associated with the 3 MGO events during the demo period. So overall, it shows enhanced MGO forecast skills compared to current version GEFSv12 and CFSv2, with the performance on par with the ECMWF. So I stop here. Take question.
We're still 5 minutes behind, so we'll move on. Thank you very much. Very encouraging results. Thanks for the analysis. So next we have Sulagna Ray. Next we have Sulagna Ray from EMC talking about the ocean forecast.
Hello everybody, I'm Sulagna Ray from EMC. I'll be showing you some of the forecast results in our latest gas prototypes, particularly focusing on the week 3 and 4. I'd like to start by thanking my co-authors in this study and the whole global UFS community developers who work across different segments of these development and ranges across different institutes and universities. So I would be showing you results from two of the latest GEFSv13 prototypes, EP4 and EP5R2, showing you the forecast scale in sea surface temperature and sea surface height, focusing specifically in the week 3 and 4 forecast bias of specific variables, including sea surface temperature, sea surface height, mixed layer depth, and conclude by showing some key messages. So the EP4 and EP5R2 are the full set latest prototypes, and this is showing that brief comparisons of these two prototypes. Both are run between October 2017 to September 2019. Launched once every week and are 35-day forecasts. The main differences are in these model physics, the HR1 tag in EP4 and HR3 tag in EP5R2. It's an including advanced model physics. And the ocean and the initial conditions in EP4. For the ocean, it comes from ORS5, atmosphere, initial conditions from GFS, V15, and ice and wave from CPC and GEFSv12. These are now replaced by initial conditions in EP5R2. So both you see differences in the forecasts resulting from both the updated model physics as well as replacing the initial conditions. This is showing the forecast scale metric, the root mean square error. In SST, the red color is from EP5R2 and the blue is EP4. The lines are ensemble means and the dashed are the individual ensemble members. The black dashed line here is the persistence calculated from the observation. So for the SST, we use Ostia, and clearly you see there is not much difference in the RMSE in SST in between EP5R2 and EP4. However, it does beat persistence by D12. The bottom panel is showing the sea surface height RMSE, and you can see the root mean square error more or less persists at the same level throughout the forecast period. In this case, the EP5R2, which is the red line, do perform a bit better than EP4. So we do see some improvement in sea surface height, and it also tends to beat persistence faster than that in EP4. So starting with looking at the week 3 and 4 forecast biases, the SST biases from EP5R2 on the left and the biases from EP4 on the right. Basically, both the bias patterns are retained in both the prototypes, and that includes this warm coastal boundary warm bias, equatorial warm bias, and the south of equatorial, this cold bias just south of the equator in both the Pacific and the Atlantic. However, if you compare the intensity of the colors, this bias just south of the equator is slightly reduced in EP5R2. The other improvement is the Indian Ocean region, which has a warm bias along the equatorial region that is substantially reduced, although not gone. So the initial conditions warms up the sea surface temperatures from EP4 to EP5R2, and that kind of contributes towards reducing these cold biases over here. And also the major improvement in the reducing this warm bias over the Indian Ocean does come from the initial conditions. So this is the forecast bias for week 3 and 4 in SSH. You can clear the deep magenta colors are positive SSH bias, and the greenish are the negative SSH bias. You see large regions in the Atlantic having intense colors of negative SSH bias that is substantially reduced over here. And also the Indo-Pacific region, you have intense magenta colors that's kind of much reduced in EP5R2. Both of these are coming from the initial conditions. The SSH bias pattern more or less remains the same from week 1 to week 3 and 4. However, around the equatorial Pacific, you do see major changes in this week from week 1 to week 3 and 4, like this positive bias that increased from week 1 to week 3 and 4 in AP4, that is substantially reduced. So that's a positive improvement. However, the negative SSH bias around the dateline in the equatorial Pacific, that kind of is increasing, and it's increased compared to EP4. So looking at the mixed layer depth forecast biases, this is the forecast bias in EP5R2. Mostly these brownish shadings are indicating that we have a shallow bias over the global ocean, with the equatorial and the coastal regions showing a slightly deeper bias. There is negligible change in this shallow bias between EP4 to EP5R2 in week 3 and 4. However, if you look into the initial condition bias in the initial conditions in EP5R2 and EP4, you see much lighter colors in EP4, indicating that the biases have increased by changing the initial conditions. However, the rapid increase of the error growth of with the lead time from week 1 to week 3 and 4, that was arrested in EP5R2, and leading to the biases by week 3 and 4 between EP4 and EP5R2 to be compared. So this is showing the summer Ekman upwelling. This is from the observation, estimated from the observation in ERA5, and this is in EP5R2. You have strong upwelling just south of the equator, and this upwelling is largely represented pretty well in EP5R2, although it's a little bit weaker, and that could be tied to the fact that we have weaker southeasterly wind stress just south of the equator over here. So the other major drawback most likely is this slightly too strong upwelling that's appearing just north of the equator, which is not exactly there in observations. This is showing the zonal current forecast biases, and you can see where that the two strong westward surface current biases have further degraded from EP4 to EP5R2. And the biases develop from week 1 onwards to week 3 and 4, peaking in week 3 and 4. And this bias seems to be larger than that in EP4. If you look into the subsurface, the equatorial subsurface along between one south and one north, and look at the zonal current biases, that's pretty much minimal in week 1. However, it increases with lead time to week 3 and 4, leading to this stronger westward bias near the surface, and slightly too strong equatorial undercurrent. And by week 3 and 4, this kind of likely indicate that it's going to increase the vertical current shear, which likely could affect the upper ocean mixing and the temperatures as well. So with that, this is the some of the messages that I would like to convey is improving the initial conditions did improve the sea surface height, and also this SSD forecasts, particularly in specific regions. The error growth in mixed layer forecast is arrested in EP5R2. However, we still need better initial conditions so as to reduce the bias in the very first place. And the equatorial biases do grow with lead. So just improving the initial conditions perhaps is not enough. We need to do a little more in terms of before fixing the model. For example, the sea surface height biases has increased with lead, particularly around the dateline, and the surface and subsurface zonal currents shows some deterioration with lead, particularly increasing this vertical current shear. So with that, thank you, and you can email me or ask me any questions. Thank you.
Do we have one quick question? We're almost caught up in time. Yes.
Yeah.
Please go ahead. Yeah.
I have a question for you, but also for the first speaker. Is EP5R2 compared with before has several differences. All of them have the same ocean as the modern template, but there are changes in the physics and changes in the aerosols. Both of them will affect have large potential to impact the atmospheric circulation. So I have two questions: is how expensive the aerosols are, and if they seem to have a strong impact on the surface winds and the currents, what is the strategy for further tuning?
Want me to take that?
Sorry, is that I'm trying to understand.
Yeah, go ahead, Avatar.
So the question was about differences between EP5R2 and EP4. And one question is on the expense of adding aerosols. And the other one is what changes were brought in, which are leading to those difference in the performance in the forecast time. So yes, physics changes, aerosol plus initial conditions are different. So we for the EP5R2, we are using what we call the replay conditions. We got this replay using ERA5, using ERA5 and ORAS5. So that's a big difference as well. In terms of the expense of aerosols, roughly I would say they're adding 30 to 40% more to the expense of running EP5R2 compared to EP4.
Thank you. The reason that we asked is because before it was mentioned that the testing, because of the expense, it slowed down the testing of the complications. So.
Yeah, thank you. All right, next, we'll have another presentation by CPC, Laura Ciasto, talking about the stratosphere. Thank you.
Yes, we are going from the ocean to the stratosphere. So we're literally going to end on a high note. I also realize we're running a little over and there's a happy hour after this. And I do not want to stand in the way of people and nerdy science talk over a beer. So I'll try to keep this quick. So I'm going to talk about one specific aspect of the stratosphere today. I'm going to be talking about the Northern Hemisphere stratospheric polar vortex, because this is something we use a lot in S2S prediction, especially at CPC, our week 3-4 forecast. So understanding how this is represented in the models is quite important. So just to define the polar vortex, in case you don't know what it is or why we care about it, we're talking about zonal mean, zonal winds at 10 hectopascals, 60 north. There's also one at 60 south. And why we care about this from an S2S prediction standpoint is that polar vortex variability can have impacts down to the surface. And the one we know people hear most about are sudden stratospheric warmings. So these winds at 10 hectopascals, which are typically westerly, when they slow down and become easterly, this is what we call a sudden stratospheric warming. And the effects of this can propagate all the way down to the surface. And when it does, it can increase the odds of a cold air outbreak over parts of CONUS. So from a forecast or a prediction standpoint, this is obviously of interest to us. And overall, the polar vortex can be a good source of predictability, just partly because it's not the tropics, which we are always relying on, NJO. And so when those are quiet, what do we have? So hopefully the stratosphere. And also the time scale on which the stratosphere variability is operating, the time it takes for it to impact the surface also makes it an attractive source of predictability on these S2S timescales. Now, that said, there are challenges with this. All that cool coupling and cold air outbreaks we talk about are difficult to really capture because the coupling impacts timing. These aren't sure things. And the bottom point is the one I want to focus on most, which is the fact that the dynamical models are somewhat limited. Yes, we can predict these out to about 14 days, but the issue is that some biases in the models can inhibit our ability to even harness this 14 days. So I'm showing this example here from the GEFSv13 evaluation that Zach Lawrence did. And it's known that GEFS-12 has this westerly wind bias. So the polar vortex westerly winds. In GEFS-V12, it is even more westerly. So what this means is that in the top panel there, he's showing the hits, misses, false alarms for weak vortex events, such as sudden stratospheric warmings. And what you can see there in that light, maybe you can see a pink line, is that the misses really dominate. So it's under predicting those sudden stratospheric warmings because the vortex is too strong. On the flip side, it's over predicting the opposite when the vortex events because it's already strong enough. So what does this mean in sort of a forecast setting? Like how would this affect forecasters? So what I'm showing here are forecasts related to the February 16th, 2023 sudden stratospheric warming event. So how well was GEFS able to provide information about this to guide CPC outlooks? So I focused on two. I focused on the February outlook and the week 3-4 outlooks. So what you can see here, this line, and I don't think you can see the other one, there's a dotted line here. Those are relating to the U10 outlooks around the time that we were making the initial February monthly outlook and then the updated outlook. And what you can see over here is it's not getting the sudden stratospheric warming. And in fact, it doesn't actually start to see the sudden stratospheric warming till February 3rd. So a little bit less than 14 days, but not enough for it to be seen in the February outlook. So this is not even mentioned in our February outlooks. So impacts are not going to be discussed either. For the February 3rd and the February 10th, they both give an indication of the SSW, but it's underestimating that strength. So if the models are struggling to predict the SSW, then their subsequent impacts are also going to be affected. So this is what one thing we want to look at when it comes to all of these EP evaluations and prototypes. I'm not going to go through all of this. I'm focusing on one aspect. This was the full evaluation that I did. I'm going to focus on the things in red here. So I'm really only going to talk about zonal wind, the Northern Hemisphere polar vortex. The big caveat here, and previous talks have kind of mentioned this, this is only a 2-year run. There's only so much you're going to be able to conclude. It's more of a sanity check. And one of the nice things too about these particular runs is that there is a sudden stratospheric warming in both winters. So that does give us some indication of how well GEFSv13 is able to capture this. And I am verifying this against the conventional observational reanalysis, which is the NCEP's latest reanalysis data set. So what I'm starting with here first, I don't know that you can see all these lines, but that's all right. So these are the zonal wind biases for November to March initializations. And I don't know that the lines are showing up very well, but the contours would show the climatology. That's where you'd be able to see the polar vortex and the shading showing the biases. So the left is EP5, the right is GEFSv12, and then I've got the week 1, week 3, week 5 forecast. And the good thing is the green is showing up because that's the westerly wind bias that you can see here in the GEFS for the Northern Hemisphere polar vortex. And what is promising is that while the wind bias is still there, but it has been reduced. So we're moving in the right direction there, which we want to see. And I'm not going to talk about the Southern Hemisphere just for the sake of time. It's interesting, so you can ask me later. This is the same idea, but for zonal temperature. And the few things I want to point out here is one, you can see in GEFSv12, this red, there's this pretty substantial warm bias that you see in GEFSv12. And the amplitudes are definitely reduced. The warm biases tends to be confined now to about 10 to 20 hectopascals. We do, however, see more of a cold bias in this region. The other thing I wanted to point out is there's more of a cold bias along the tropical tropopause. You can't see the lines probably. This is also reduced. And then finally, the Northern Hemisphere polar cap. This cold bias that you would expect to see with the strong westerly bias is definitely reduced at least around 10 to 20 hectopascals. So once again, moving in the right direction. what does this mean for, sudden stratospheric warming? So what we're looking at here now is just the polar vortex. So it's still pressure, but now this is a forecast step. And I've divided this into the 2 winters. So there's a sudden stratospheric warming in each winter, but you can see the evolution of the biases. So for 2017, 2018, you can see this enormous westerly wind bias that is reduced in the EP5. And then for the second winter, you see, especially at longer lags, the amplitude of the biases are about the same, but they are reduced a little bit when we get to the shorter lags. So once again, some improvement there. Okay, so what does this mean for prediction of sudden stratospheric warmings themselves? So what I'm showing here are the SSWs for both winters, and I've plotted the forecasts for the 3 weeks before and the 1 week after. So the idea is like, at what point are they able to see the sudden stratospheric warming? Now, keep in mind, they're only 1 week initialization, so the temporal resolution isn't great. But what we can see for February 12th SSW is that the GEFS is starting to get this around February 7th, so about a week ahead of time, whereas EP5, you start to see it around the 1st of February. So it is getting these SSWs a little bit sooner. Both are able to predict the evolution once the SSW has started, but the recovery is a bit slow. For the 2019 case, which happened just after the first of the year, GEFS starts getting it about a week ahead of time. So EP5 actually starts to see it. So the EP5 is all like the reddish colors. You can see that even as early as the 12-13 forecast, it's starting to get it. It does not, it struggles with it. It's not as strong as it should be. This could be related to the fact that there is still a bit of a westerly wind bias there. But you can see once the SSW has occurred, with the red and the blue lines, both GEFS and EP5 are able to get it. So just finally a bit on the stratosphere-troposphere coupling. People really like to see these paint drip plots to understand whether or not models are getting this coupling. So what I'm showing here are polar cap anomalies for geopotential height for EP5, GEFS, V12, and then the core reanalysis. So I'd say for 2018, neither model is really capturing the coupling quite right. So you kind of see this paint drip feature in core. You see it a little bit in GEFS V12, but it's well after core is showing this, and then EP5 doesn't really get it at all. For 2019, there's not much coupling even in the reanalysis. GEFS V12 is not really seeing it at all. You do see it a bit in EP5, but it is a bit weak overall. So I don't have a conclusion slide, I have a report card. I've only talked really about what is shown here in the blue. This is the other stuff that I've evaluated. We are overall seeing a reduction in these biases. It does seem to be improving our ability to predict these sudden stratospheric warmings. That said, just to caveat the way others have, this is only a 2-year run. So, a lot more to look at when the full Hindcast comes out. And that's it. Thank you.
Good. Can I ask a question, or are we running spear?
Yes.
I was just gonna comment, don't be so harsh. You're talking about the 2018, and the thing is you only have a handful of ensemble members, and reality has one ensemble member. And that noise that is, the paint drip is some sort of signal to noise ratio that's low in the troposphere. And it's very easy to misinterpret that on a small number of samples. Does that make sense?
Yeah, no, it makes sense. And I would also caveat too, the way I did that stratosphere-troposphere coupling with the anomalies is admittedly a bit dodgy because I don't have full Hindcasts to remove the climatology. So I'm using core, not the way you would do that in an operational setting, more just a gut check to see what it's looking like. Yeah.
All right, thank you very much.
Yep.
Yeah, this is a great session. Thank you for all the speakers. Let's thank them one more time. And then for those going to Denison, let's continue.